So you can see that some people are getting the answer. Okay, your region is correct. I think, yes, I can see your answer, Damilola Aruna. And Damilola Aruna is okay. Several people, yes, have gone it. So you can see again, you can see how we can take the trace of a gradient. When we take the trace of a gradient, what we get is called the divergence. So that is the definition of the divergence. Temperature and other scalar fields cannot have divergence because their gradients are vectors, therefore cannot be contracted. You cannot take the trace. The gradient of a vector field, such as a velocity gradient, can only be contracted in one way. It has only one possible trace. Gradients of larger objects, such as tensor fields, can be contracted or traced in more than one way. In that case, the disambiguation rule for contraction to obtain a divergence is to contract with the basis that came from derivative. For example, for a vector field, the gradient Vx, the divergence is this. So this is what you have all got right now on page 17. You can see it here on page 17. Is Vi, Ix, and it is dV1 dx, dVi dxi, which is the V1 the x1 the V2 the x2 the V3 the x3. Now, when it comes to, okay, so, but if it is a bigger object, then it becomes a little bit, we will talk about those ones later on. The curl of a vector field. Now, I have given a much larger definition of a curl. I want to reduce the definition to, I want you to read pages 18, 19, and 20 if you like. But I want to omit all those things and define curl the way most textbooks define it as this last quantity here. The curl of a vector field, the curl of U, is simply this quantity here. The curl of U is this quantity. What I am doing is to prove it is so in the earlier 2 pages. I don't want to spend time. And then from there, you can easily show that if you take the divergence of the curl, you are going to get 0. So the divergence of the curl is going to be 0. That is proved here. And I don't want to go through the details. I want to just take what you will get in most of the books at your level is just that the curl is this quantity. That's all you will get. Most of the books you will see at the 300 level or at undergrad level will not do more than that. So forget about the other ones for now, so that we can move on. So we have now reached page 21, where we can now talk about the parametrization of isosurfaces. We can talk about parametrization of isosurfaces, and one example we have here is in this example, I am guided by me buying oranges at the second gate. There are people who will peel your oranges for you, and we open a slit there in this conical form for you to drink your orange. So I am saying that the orange itself is approximately a sphere, so you can see the surface of the sphere. When they put the knife in and they cut this thing out, you see a new surface is introduced and a cone is taken out of it. Now, I can deform that cone. and have other surfaces. Because when we are talking about surfaces, we are not necessarily talking about simple, easy surfaces. It might be the surface of a deformed object like this. Now, engineering reaches that conclusion at that point very easily, because it may be that you even have a code to start with, and because of stresses, the thing gets deformed to this stage, and you want to still do some analysis of the displacement and the stresses around the source. So you are left with something as complicated as this deformed thing. So what we want to do is to be able to define and parameterize these surfaces in a consistent way so that we can analyze them. So one easy way to parameterize surfaces is to use the coordinate systems. You can use this. You'll be surprised that you can use Cartesian coordinates to parameterize surfaces. And what I'm going to do, I'm going to take some curved surfaces, like I'll take the surface of a sphere, And I will show you that you can use Cartesian coordinates to parameterize the surface. So after parameterizing the surface with Cartesian, then I will parameterize the surface with spherical coordinates. And you can see that you can parameterize in any way you like. So it may look contradictory, but you can see it will happen. The lines we are seeing here are the isosurfaces of this thing, where one particular parameter is constant. Like now, in this case, all those things round and round and round are the constant lines of theta. And all the cones that you can get to the center here are all the cones you can get to the lines here are those thetas as surfaces. That's what you have there. But if you take a slice through it, those are the surfaces of phi. Those are the surfaces of phi. If you take a slice, and then if you take shell upon the spherical shell upon spherical shell, those are the surfaces where R is constant. So what happens is that when a particular object has 3 dimensions, if you fix one dimension out of the 3, you get a surface. For instance, here, if you fix the radius, you get the surface of a sphere. If you fix theta, you get the surface of a cone. And if you fix phi, you get a plane. And if that is not obvious, I will show you again when we get to the 3D spherical coordinates showing. This page 22 is a repetition of what we have gone over and over, how we move from Cartesian to cylindrical to spherical. That is what we are doing here. You can see that. And then here are the isosurfaces of in the cylindrical polar coordinate. In the cylindrical polar coordinate, the round areas are the areas where R is constant. The concentric circles on the flat surface are the areas where Z is constant. And then the planes that are cutting to the center of the axis of this thing, those planes are the areas where theta is constant. So it is important for you to know that what we call surfaces are, you just keep one. If you keep one out of 3 coordinates fixed, you get a surface. So a surface is a function of 2 variables because the 3rd variable is fixed. So usually we use the remaining 2 variables that are not fixed as the parameters. We can use other parameters, but those are the simplest parameters that we can use. And sometimes you may prefer to use those simplest parameters. Okay, the spherical polar coordinate system is 3 ordered triplets with a different strategy. And then we've done this before. You remember here now, so you can see that when your rho is constant, you get the surface of the sphere. When your theta is constant, you get the surface of a cone. And when your phi is constant, you get a plane. Those are the 3 isosurfaces for the spherical coordinates. And you can get the position vector of an arbitrary plane. Know that position vector is R is equal to xi plus yg plus zk. Now, if it is a plane, you see that Z is, let us say you keep Z constant, and you can express Z in terms of x and y. If you substitute, you can see that the position vector is now a function of x and y. Similarly, you can parameterize a cone that way, and you can see again that in the cone, the Z coordinate in the cone is related to x and y as the square root of x squared plus y squared cotangent of theta. And therefore, you can see that on the surface of the cone, again, is a function of x and y. Just always know that we can always reduce the number of variables to 2 and get a surface if we keep one of the surfaces fixed and express that fixed surface in terms of the others. We are now going to get a parameter of x and y. That is how surfaces are defined. So let us take a look at this. Let us look at this particular case where we have x-axis going this way, y-axis going this way, and z-axis almost pointing upwards here. Now, if you have x and y here, if you project them up to the curved surface of the sphere, this is what you get. This is x0, y0. This could be x1, y1, and so x is equal to y, y, and so on. And this could be x is equal to r, y is equal to 0. And here is y is equal to r, x is equal to 0. And if you draw the iso lines, this is what you are going to get all around. And at that point, you can now, if you now want to define the curved surface, look at how we can define the curved surface and pay attention here. Pay attention here on this curved surface. Let us say we take point P, Q, and R. Look at what happens to point P, Q, and R. I hope you can agree with me. Let me, please, I want enough people to indicate agreement before I move on. I put it to you like lawyers do, that P and Q have the same value for X. Can you, I want to see if there's agreement, whereas R and P have the same value for Y. Can I have agreement on that? If it is clear to you, say so. That if we are parameterizing this with X and Y, P and Q have the same values of X, P and R have the same values of Y. Okay, let me see whether I have agreement on that. Okay, so I have enough people who can see that. So if you cannot see, so that means that if I'm moving from P to Q, it's only Y that is changing. If I'm moving from P to R, it's only X that is changing. That is what we are saying here. So in defining this elementary area, we can make this area as small as possible. And I want you to look and geometrically see that as Q approaches P, if we continue moving Q as close as possible to P, the line PQ becomes a tangent that is in direction of Y. The line PQ is a tangent that is in the direction of Y because X is not changing. Can that be seen? If we keep making PQ smaller and smaller, you know it will almost become a straight line. And it is now going to, when it is very close, it's now a tangent. And it's a tangent parallel to Y. Because only Y is changing, there is no variation in X. Similarly, as R tends to P, what is there is also a tangent parallel to X, because Y is not changing on that. Consequently, if we want to find an element of area on that surface, if I want to find an element of area on that surface, I'm almost telling you what I will do. But I want, first of all, I want us to see how many people can see that as Q approaches P, we are going to get a tangent. PQ becomes a tangent here. And as R approaches P, PR becomes a tangent. I want to see how many agreements I have on that. Please let me see, show if you agree with that. Okay, good. There are enough people that can see that. Now, I want to ask another question. If I want to find an element of surface, given that I have two tangents on the surface, what can I do that will give me that area that I'm looking for on the surface? What can I do? Now, this is a method that most of your textbooks try to avoid. And if you understand it, you have a much deeper understanding of what's going on. They bring all sorts of formulas. But there is something very, very interesting and elementary almost here that makes the things even very attractive. If I want to find the area of this blue surface, and the area becomes very small, how do I find it? There is something very easy. There's a very easy way to find it. I want to see if somebody can recognize that. Okay, Ajibola has got it. Ajibola says we take the vector product, because if you have this, if this is a surface vector and this is a surface vector, they are two non-collinear vectors on the surface, and the cross product of those two vectors will give us the magnitude as well as the direction of the vector area. This will give us the magnitude, this cross this will give us the magnitude as well as the direction of this vector area as the area becomes very small. Fantastic. So those of you for whom it is not obvious, think about it. I'm going to move on now. I'm going to reparameterize the space using some other means. See, I parameterize this surface using X and Y. I don't want to use X and Y again. I want to use other things. For me to use other things, remember that if I use spherical, I could have used symmetrical, but let us just use spherical. If I want to use spherical polar, you can see that this the outward growing something is rho, and then the vertical angle is the theta, and then the horizontal angle is the phi. Okay. Suppose I parameterize using rho, theta, and phi. Notice that on the surface, rho is constant. So rho doesn't play any part because on the surface, rho is constant. So we are only looking at, I said theta and phi here. It actually should be psi. It actually should be theta and phi to be consistent. Let me see, let me edit this. Let me edit this because it's going to cause confusion with something else. Phi. Okay. So you can see that along R and P, what is constant? Along R and P, I will say that phi is constant along R and P, but along P and Q, theta is constant. So the point P and Q are on the same slide through a plane with constant value of theta. Similarly, points P and R are on the plane with the same slides with a constant value of phi. To show this explicitly, we can say P is theta 1 phi 1, Q is theta 1. Oh, okay, no, it cannot be theta 1 phi 1 because P and Q are on the same slides. So theta is constant, but phi is not. So it is theta 1 phi 2. Okay, so let me go and project this thing now. Slideshow. Okay, we're here. So P is theta 1 phi 1, Q has theta 1 phi 2, and R has theta 2 phi 1. So from P to Q, what is changing is from P to Q, what is changing is phi, and from P to R, what is changing is theta. There's somebody raising a hand. Let me see whether we can accommodate that. No, you please don't raise the hand in this class. Instead, just put whatever comments you have in the chat room. I don't have the time to attend to hand raising there. So put a comment on the chat room. If I have time, I look at it. If I don't have time, I take a look at it after the class. So you have that. So what we are going to do now is that you can see that it doesn't matter whether we use X and Y or theta and phi, we can always parameterize a surface with two variables. That is what is important. We can always parameterize a surface with two variables, and the lines, the iso lines on that, one of the variables is remaining constant on those iso lines. That is the issue that is consistent. So it does not matter what you are using to parameterize. What is important is that when you parameterize a surface, you use two variables, and on the iso lines, one variable is constant, the other is changing. So we can therefore get a preliminary result that will be very, very useful in our understanding of Green, Stokes, and Gauss's integral theorems. We are going to take an arbitrary surface now. That arbitrary surface, P and Q. What we are going to do is that we are going to have P as a point, and we are going to put Q on one isosurface, and we're going to do something that will surprise you. We're going to look at what happens when Q approaches P. Then we put, after we have gotten a result, we put Q again on the other isosurface, and we allow Q to approach P again. And we're going to get interesting result that will show us how to get the element of area on that. We have already seen what the result should look like in what we have done. This is now for us to go and actually make it happen. And before I go on, let us see where we are going. What are we trying to show? I think I want to move on from there. Integral field theorems are needed to derive the governing equations of continua. And continua, it can be fluids, it can be solid, it can be anything that an engineer is working on. The most relevant results are often associated with the names of Stokes, Green, and Gauss. These theorems are related to one another in several ways. Our practical uses are emphasized here. We are not interested in proofs and esoteric issues. We want to know what these theorems state, and how to compute them and gain some skill in computation of the issues that help us to calculate. That's all. Can we use them for calculation? Can they make our calculations easier? If they can we use them? That's all. So let us begin by stating the Stokes theorem. Before you state the Stokes theorem, let me just show you this thing that looks like a joker's or a fool's cap. It is like a fool's cap. You see, this is the rim of the cap, which I have denoted as gamma. That is going to be the path of an integral. That's that curve. And then the surface of the cap itself is what I labeled as S. And the what color is this now? Can this be orange or, well, I don't know. I'm colorblind. I don't know whether it's orange or yellow. That thing that looks like orange or yellow or gold, whatever you like, is inside the cap. So let us, and then at any point, the end here is an outwardly drawn normal. So Stokes theorem is addressing a situation like this. And let us see what Stokes theorem states. And then we will now try to understand what it states and how to use it for computation. Once we are able to do that we understand how to compute things with the Stokes theorem, then we'll go to the Green's theorem, which is a special case of Stokes. And then we'll go to the divergence theorem of Gauss. And then by the time we have done that, we have looked at the most important integral theorems for working with fields. Consider a surface with a boundary curve as shown in the picture. What I'm going to do next is to tell you what is positive and what is negative. The outwardly drawn normal is in such a way that a traversal of the boundary curve in the direction shown keeps the surface on the left-hand side. So let us say you are here and you are walking along this boundary. As you go through, you will see that the surface is always on your left as you go around. So such a surface is said to be positively oriented. That means if you go in the other direction, you are now making surface negatively oriented. All that will happen, you are still going to get the same numbers, but you are going to get negative. That's all. Or if you now have the outwardly drawn number pointing in the opposite direction, the two negatives will cancel each other. So that is, so you can always, this is just for sign convention. It doesn't have anything to do with the value of what you get, but it's important. So a surface is said to be positively oriented if when you go along the rim, the outwardly drawn number to the surface you are saying is always, that surface is always on your left-hand side. So that is what we will define as positive. There is nothing sacrosanct about it. Another person can come and define that as negative, and that will be okay. But for our use, this is what we will define as positive. Stokes theorem relates the integral of the curve of a vector or tensor field on this surface in the Euclidean point space to the integral of the vector or tensor field over its boundary curve. What are we saying? Let us see the formula. In this case, Stokes theorem says, given a positively oriented surface S and bounded as shown by a path L. See, the surface is positively oriented and is bounded by a curve. It ends in a curve. It doesn't close. It ends in a curve. It's open. It's bounded. That if you perform a line integral along the rim, the answer you will get is the same thing as if you perform a surface integral on the curve of that same vector on the surface. That is Stokes theorem. Stokes theorem says you first of all have to know what the positively oriented surface is, which is what I've described and drawn here. You have this positively oriented surface. If you have a positively oriented surface, and you take any vector and you integrate it along the rim. You take the line integral of the vector along the rim. The answer you get is going to be the same answer as another person who takes the curl of that vector and integrates it along the surface. So the line integral here coincides with the surface integral here. So the question is, how do you perform a line integral and how do you perform a surface integral? So I'm going to spend the rest of the time not proving whether Stokes theorem is correct or not, but instead I will compute, I will choose a vector and I will choose a path. I will perform a line integral. Then I will take the curl of that vector and I will perform, and I will choose a surface that ends in this rim, and I will perform the surface integral. When I do that, you will now know how to actually compute a surface integral. That is the best way to really introduce the surface integral. So for you to get a surface integral, you must be able to define an element of surface. That definition of the element of surface, that is what I was laboring to do here, and that's what I labored to do here. So I've already given you a hint of how to find that element of surface. Once I found that element of surface, we will now use mathematical. Given any, I will use some functions. You will now go home. You will change the functions to any functions you like. And you will now try to show that Stokes is correct by first of all performing the line integral around the rim and getting an answer, and taking the curl of the same vector that you had before and performing the surface integral along the surface and see whether the two results will be the same. As those two results are the same, and by the time you do 5 examples, it would have registered in your mind what Stokes is talking about, more than any cram that you can do, more than even any proof you can do. I will show you, I will write the code for you. In your own code, all you will do is just be making alterations to my own code. But that is not a trivial step. If you can do that and you can get your own answers, then you are learning to use mathematical, you are learning Stokes theorem, and you are learning a major idea of an integral theorem of calculus. I'm not going to, I'm already on page 34. This slide is ending on page 55. I'm not going to go through everything today, but I'm going to whet your appetite so that we know how to prepare. And I'm hoping that some of you will read the whole thing, so that by the time I'm teaching this thing next lecture, you will be even much more attentive and you ask me deeper questions than you can ask now. But let me just show you something. You see, let us say this is the curve that is of interest to us. This curve can be bounded. The surface we are interested in can be this disk. Are you seeing the curve and the disk? Admin, can you see my curve and the disk? Can you see 3 pictures on this page?
Yes, sir. Yes, I can see.
Okay. So in this picture, let us say this is the curve. Well, we can choose the surface as this disk, as this plane here. That is one surface that has this as its rim. Another surface that has it as its rim is this conical face here. This conical face also has it as its rim. Or you can still use the same rim and have this spherical surface and having it as its rim. So what if Stokes is right? If we perform the line integral here, and we perform a surface integral on this disk and get a result, we perform the same surface integral of the curl on the, we perform the surface integral of this curl on this surface, we perform the surface integral of this curl on this surface, we perform the surface integral of the curl on this surface. Those 4 results, no matter what function we started with, those 4 results should give us the same answer. That is what Stokes is saying. And because that's what Stokes is saying, I am going to use mathematical, and we will together compute the thing, and you will now go home and you now choose other functions, and you will see that all those 4 results will always be equal. Then you now know that Stokes knows what he's talking about, that the line integral along the is equal to the curl of the functions on the surface integral along the whole surface. That will be Stokes theorem. Once we have done that, we will now specialize the Stokes theorem to Green's theorem by now collapsing it into 2 dimensions instead of 3 dimensions. After that, we will be ready to look at the Gauss divergence theorem. That is what, those are the things we are going to do, and we will do them after I've given you time to digest the little that we have done now. I think I even though I still have a reasonable amount of time, let me see how much time do I have. Oh, it's not even a lot. I have basically 10 more minutes really to go. And since you have been so attentive, I think it may be a good idea to let you go and rest. And some people are ready. We started the class at the peak. We had about 280 people. We have 166 people still on. So nearly 120 people have jumped ship. So before I lose more of my clients, so I better let you go before you all resign and leave me alone in the class. So, ladies and gentlemen, it has been a pleasure having you. So welcome back from the holiday, compulsory holiday you have been in. I hope we can finish this. I hope we can learn more and enjoy to learn. And my hope is that we enjoy what we are learning, that it's not just going to be drudgery or just the fear of exam. I hope you will be aiming to get an A in my course. I like people getting very good grades in the course. That's why I give you all the examples that I'm giving you, and I warn you the kind of things I will set in the exam ahead of time, and I will give you opportunities to test yourself on the website before the final exam comes. So I will take a look at your, or maybe since we have a little bit of time, let me see what kind of, there's a lot of reporting on the, okay. So let us see what will happen. And now I'll be willing, if you want to meet me physically, I'll be willing, if you can arrange that on Thursday, on Wednesday evening or Thursday evening, I will be free to see you. So if you want to see me and you can arrange a classroom or an amphitheater or a place where we can actually sit face to face and talk about things, reach me through your class rep. I'll be able to arrange that for Wednesday or Thursday. If not, we continue meeting this week, video. I mean, Wednesday, after tomorrow, and Thursday. If you want, it doesn't have to be any serious thing. It could just be to chat. It could just be to see one another and see. Some of you already know what I look like. That's not important, but just in case. And maybe I will need to see what you look like. So, because the last time we tried it, I think, I don't know whether it was this class or a class, the NEPA took light and we were in that place. I didn't like that. But if you can arrange for a chat, I would have said maybe we should just go and grab a drink, but I don't have enough money to, you know, I've been hungry for 8 months. I'm almost dead now of hunger. I've been fasting for 8 months, so I have no money. If I had money now, I would have taken you to one big place and we can just have a drink. But have a nice day, and please read the rest of the notes so that we'll be better prepared for the next lecture. Thank you very much. Bye-bye. Oh, sorry, there's a question here. Some of us still don't have access to the self-test. Well, please, the office people can answer to that.